to start the ball rolling and to introduce you to some of the key concepts of game theory, what I'm going to do is start off with a class of game where the players involved, that is the people who are involved in these strategic interactions, who are playing this game, choose their actions at the same time. That is, the type of games that we're going to be looking at are what are called static games. Static games are games where players choose their actions simultaneously at the same time. But we're also going to look at these static games where the players involved also know perfectly the benefits that accrue to choosing certain actions. And they know not only the benefits that accrue to them, they also know the benefits that all other players in the game get from choosing a certain course of action. That is the game, this type of static games we're going to be looking at are also static games of complete information. So the benefits or otherwise of choosing certain actions are known perfectly to all players within the game. Now later on in the module, we're going to look at different types of games. We're going to look at games where players do not choose their actions at the same time. We're going to look at games where there isn't complete information. But as a starting point, most simple rendition we can do, static games of complete information. Now within this context of this class of game, this type of game that are static with complete information, I'm going to introduce you to the very, very staple of game theory. The first game you'll see on any game theory course. And that is a game, hopefully, that you've already touched upon in previous lectures, in previous years. And that is the idea of the prisoner's dilemma. Now, the prisoner's dilemma is an absolute classic game. And it's important that you're able to understand it and reproduce it. And if you think about the assignment, what was it all about? In the context of a repeated prisoner's dilemma. Well, we're not going to do the repeated part until a number of weeks hence. But we're going to start off, you need to know what is the prisoner's dilemma. What are the incentives within the game? What are the outcomes of the game? So, this is the starting point then, the prisoner's dilemma. Now, I'll give you the original exposition of this game, where there quite literally are prisoners involved. And in this game of the prisoner's dilemma, there are two suspects who are charged with a crime. The point is, the police don't know for sure that they've committed the crime. They only suspect that they have. So what the police do is they arrest them and they bring the suspects in for questioning. The problem is for the police, because they don't know that they've committed the crime, because they don't have any evidence to convict these two suspects, they need at least one of the suspects to provide a confession. So, how do they do that? How do they elicit that confession from the prisoners? Well, the way that they do it is they bring them in and they take them to separate interview rooms. And they speak to them and they explain to them the consequences of their actions. So these suspects can do one of two things. They can either confess that they committed the crime, or they can completely deny involvement. But what will run through all of this, and this is where students, if you're going to make a mistake in an exam, in your coursework, it's setting this game up properly. The prisoners can confess or deny. But the nature of the confession, it isn't I committed the crime. The confession is we committed the crime. So by confessing, you're not implicating yourself. You are saying collectively that both of you committed the crime. So, these suspects have one or two choices. Do you deny or do you confess? So, the police take them to the respective cells and they explain to them the consequences of what happens if they deny or confess. So the first thing is if neither of the suspects confesses, that is, if they both deny involvement, the police don't have the evidence that they require. They require at least one confession, and neither of the suspects has given that to them. So there's nothing that the police can do. And so what happens is they give them a nominal 1 month in jail. They convict them of some minor misdemeanor. So that's if they both deny involvement. Neither provides a confession. So that's one option. The alternative, or an alternative, is what would happen if both of the suspects confessed. They both held their hands up and said, it's absolutely true, we committed the crime. Well, then the police have those confessions that they need. They only needed one confession to have the evidence, but now they've got two. Both of the suspects have implicated themselves, and they both get 6 months in prison. So these are the straightforward scenarios, where they both deny or they both confess. What about when one suspect denies whilst the other confesses? Well, under this scenario, the police will have that confession that they need. So, the suspect who confesses tells the police, it's absolutely true, we did commit this crime. The one who confesses is released absolutely scot-free. They don't spend any time in prison. They've given the police the confession that they require. They've helped the police with their inquiries. And because of that, they are allowed to leave without spending any time whatsoever in prison. So that is for the one who confessed. The one, though, who denied, said, look, we didn't commit the crime, nothing's happened. Well, the police know that something has happened. The police have the confession from the other person. And so that person who denies involvement in the crime, whilst being implicated by the other person, will now receive the full service, the full severity of the law. They will serve 9 months in prison. So that's the nature of the prisoner dilemma. It's a very, very simple game. Do you deny or do you confess? If you both confess, you both get 6 months. You both deny, you get 1 month. But if one person denies, whilst the other person confesses, the person who confesses spends no time in prison. The person who denies spends 9 months in prison. Very simple game, but you'd be astonished how many mistakes can be made in that initial setup. Okay? If you remember the part, deny or confess, the confess is, we committed your crime. You're not implicating yourself. Remember that. Hopefully you won't make mistakes come a later point. So, that's the game that we've set up. We can represent it in the following matrix. Now this following matrix, we have our suspects, suspect 1 and suspect 2, and these two players can choose over 2 available actions: to deny or confess. Deny or confess. And when the suspects choose a combination of outcomes, it then leads to a certain time in prison. So, for example, we said if both suspects denied involvement, what could the police do? Not an awful lot. They would convict them of some minor charge, and both of the suspects would get 1 month in prison. So that's the top left-hand cell. Alternatively, if both of the suspects confess to the crime, they would each receive 6 months in prison. And these, I should actually say what these numbers represent. These numbers represent the number of years in prison, but I've just put the negative sign in front to reflect the fact that spending time in prison is a negative thing. That prisoners would rather spend less time in prison than more. So just to make sure to reinforce this idea of the ordering of these numbers. So there you go. If they both confess, each will spend 6 months in prison. What about these two corner points here? Bottom left, top right. Remember what the game was. This, for example, that cell in the bottom left, that is suspect 1 confessing, while suspect 2 denies. And we said the person who confesses is let off with 0 time in prison. The person who denies gets 9 months. So the way that I put these times in prison is a 0 first, and then the 9 months second. This means that suspect 1 gets 0 months in prison, and suspect 2 gets 9 months. Now, by convention, the way in which these outcomes are presented is with the first figure will denote the payoff or the outcome for the role player. In this scenario, the role player is suspect 1. The second figure will be the payoff to the column player. In this case, suspect 2. And so, if we look at that top right, that means suspect 1 would get 9 months in prison, and suspect 2 would get 0 months in prison. So if suspect 1 denies, while suspect 2 confesses, 1 gets 9 months, 2 gets 0. So that's the way in which conventionally you should not just present but also interpret these numbers. The first figure is for the role player. The second figure is for the column player. So the way that I've now represented this game graphically, that is known as the normal form representation. It's the classic way of representing a static game. This game where the players are choosing their actions or moving at the same time. And regardless of what the game is, if we're going to represent it in its normal form, there are 3 key bits of information that that normal form representation will give us. Firstly, we have the players involved. In this case, suspect 1 and suspect 2. Our normal form representation always has to have that. Secondly, we'll also have the strategies available to our players. So our players in this game, suspect 1 and suspect 2, are choosing over the potential options, the strategies, of deny or confess. So there you go. That's the second aspect of our normal form representation. The third aspect, and the crucial aspect for all of this, are the payoffs that the players receive from any combination of strategies. And that's what we've just talked through. So, for example, if they both denied, they'd both get 1 month in prison. If they both confessed, they'd get 6 months in prison. So all of these various strategy combinations, we then put these numbers in here to represent the payoffs for the players. Now, the way in which I formulated this at the moment, the way in which I've set this game up, is that these figures refer to number of months in prison. But more generally, I mean, this is just this specific example, but more generally, what these numbers will represent and where these numbers will come from would be from an individual's payoff function. They will look at what's important to them, what actions they're choosing, what their rival is doing, and that will give them a certain payoff as derived from a payoff function. Now, the way in which you should view or interpret, think about a payoff function is analogous. It's exactly the same as a utility function that we would have covered last year in intermediate micro. In a utility function, when we're looking at that theory of consumer choice, individuals choose over bundles of goods. And if they choose a certain bundle of goods, it gives them a certain utility. Well, what we've got here with a pair function is not individuals choosing over bundles of goods, but rather we have individuals choosing certain actions, certain strategies. And these strategies give them a payoff. And that's what these numbers represent. So, let's think about it. Let's say an individual, and this is very, very simple, let's say an individual has 3 actions. And the underlying payoff function means that if the individual chooses action 1, she will get a payoff of 4. If she chooses action 2, she gets a payoff of 5. And if she chooses action 3, she gets a payoff of 6. Now, what basic principle would we look at? Well, when we look at the theory of consumer choice, when we look at utility functions, the idea is individuals will want to make choices such that they maximise their utility. Exactly the same here. We have a payoff function, and individuals will want to choose actions such that they maximise their payoffs. So, this individual, faced with the actions 1, 2, or 3, what would she do? Exactly. If you choose action 3, you're going to get a payoff of 6. Individuals will always want to choose the action that gives the highest payoff. Or at least they wouldn't want to choose an alternative that gives a lower payoff. So that makes perfect sense. Okay? I'm going to change it ever so slightly. Still, action 1, action 2, action 3. This time, though, action 2 and action 3 give exactly the same payoff. So if she chooses action 1, she gets a payoff of 4. Same as before. Action 2 gets a payoff of 5. But also, action 3 gives a payoff of 5. Either going to choose action 2 or action 3. But we don't know for sure, do we? So why is that not the right answer? Well,
because we know for sure they won't take action 1, that they're just indifferent between 2 and 3.
Exactly. And when, if you review the lecture capture again, you'll notice I said very deliberately, we know an individual will want to choose an action that gives the highest payoff. The next part I said, I deliberately said it really, really quickly. But it's important that you do get it. Or, at the very least, they will not choose an action for which an alternative gives a higher payoff. So what Prabhat has just said. So what do we know? Action 1 gives a payoff of 4. So what will this player do? We know categorically this player will never choose action 1. So we do know for sure something. So it isn't we don't know. What we don't know precisely, is it going to be action 2 or is it going to be action 3? Because they both give the same payoff. But we do know. They would never choose action 1. So there you go. Either of those would be potential outcomes. And it's this subtle distinction that I want you to now think about as we move forward. So we're just going to introduce very, very simple ideas. We know how to represent games in their normal form. We know now what these figures represent. And now we know how players choose certain actions. They won't want to choose an outcome for which an alternative gives a higher outcome. So, just before we move on and come back round to some more games, I want to just tease out a point that maybe wasn't as evident right at the beginning. Now, we've talked about static games, and I said static games are simultaneous move games, where players choose their actions or they make their choices at the same time. Well, let's think back to that idea of the prisoner's dilemma, where the suspects are choosing to deny or confess. It does not mean that they tell the police at exactly the same point in time, whether they deny or confess. It doesn't, these static games, these simultaneous move games, does not mean that. It doesn't mean at precisely the same point in time they make their decision. Now, these static games are also known as hidden move games. And the reason is, when players are choosing what they want to do, they're playing as if they're choosing at the same time. That they don't know what the other player has chosen to do. So the moves of the other players, the choice of the other player is hidden from them. So that means in these static games, players are choosing what to do based upon their expectations. So in the example of the prisoner's dilemma, the players are thinking, well, what is my fellow player going to do? Is he going to deny, or is he going to confess? So these expectations of what will happen, but they don't know for sure what the other player has done. So that's what we mean by a static game. It doesn't mean that they choose necessarily at exactly the same point in time. All it means is that the actions of the players are unknown to the other player before the game takes place. So that then is our introduction, though, to these static games, and that's what we mean. So, given that then, what's the point in setting up these games in their normal form if we can't say anything about the most likely outcome? So, how do we solve these games? Well, we're going to start the ball rolling by adopting a very, very simple idea. And that is something that we've already touched upon. We will say that a player, if they're rational, will never play a strictly dominated strategy. Now, a strictly dominated strategy is what we saw previously. Strictly dominated strategy is a strategy for which an alternative always gives a higher payoff. That is a strictly dominated strategy. If it's strictly, it means all of the time. It's dominated, it means something else gives a higher payoff. And so if you're rational, it's what we saw in our previous game, you never chose action 4 because it gave a lower payoff. So it was strictly dominated. And why, in the first game, did we choose action 3? Because action 1 or action 2 would pair for 4 or 5 was strictly dominated. Always gave a lower payoff. So that's the idea that we're going to adopt. And that just goes back to that very, very simple idea there that you all understood. If an alternative gives a higher payoff, that's what you choose to do. And you will always do that. So at the moment, we're not really pushing the boundaries. It's just a logical, rational assumption. That players will never play a strictly dominated strategy. So, with that principle in mind, what I want to do is revisit that idea of the prisoner's dilemma. Because we've set the prisoner's dilemma up, but it's no point in being able to set it up if we can't see anything about the likely outcome. So, that's our game that we saw, where the suspects are choosing between deny and confess. So, a player will never choose a strictly dominated strategy. So there's only two strategies here, to deny or confess. And in this prisoner's dilemma, it's a nice game to start off with because there is a readily identifiable outcome. One of these strategies strictly dominates the other. So what is it? Well, let's think about suspect 1. What suspect 1 would want to do. The suspect 1 knows whatever he does will be informed, will be dictated by what his fellow player suspect 2 does. So for example, if suspect 2 was going to deny, suspect 1 would say, well, if I also deny, I'm going to spend 1 month in prison. But if suspect 2 is going to deny, if I choose to confess, if I drop him in it, I will get 0 months in prison. And so given that choice, what would suspect 1 do? Deny or confess? Do you want to spend 1 month in prison or 0 months in prison? Exactly. You're going to confess. So if suspect 2 chose to deny, the optimal outcome, the optimal choice of suspect 1 is to confess. Spend 0 months in prison. Make sense? Okay, let's think what would happen if rather than denying, suspect 2 chose to confess. And I should just re-emphasize again, remember the way that we've set these up? The first figure is the payoff to suspect 1. The second figure is a payoff to suspect 2. So, if suspect 2 was going to confess, if suspect 1 denied, he would spend 9 months in prison. But if he also confessed, he would spend 6 months in prison. So that's the choice. Do you want to spend 6 months in prison or 9 months in prison? It's making the best choice out of those, where the obvious response is that you will choose to spend 6 months in prison by also confessing. So you can see in this prisoner's dilemma, it doesn't matter what suspect 2 does, it's always optimal. It's always a better choice for suspect 1 to confess, because you always get a better payoff. A payoff of 0 instead of -1. A payoff of -6 instead of a payoff of -1. So it doesn't matter what suspect 2 does, the strategy of confess is optimal. Or, put it in another way, what we've said, is that deny is strictly dominated by confess. Deny always gives an inferior payoff, always gives an inferior outcome. And so, a rational player will never choose to play a strictly dominated strategy, will never choose to play deny. And so, we know in this game, doesn't matter what suspect 2 does, suspect 1 will always choose to confess. Because deny is strictly dominated by confess. We said a rational player will never play, never choose a strictly dominated strategy. So, we know exactly what suspect 1 is going to do. And given the way that we've set this game up, it's completely and utterly symmetrical. So we could go through exactly the same line of reasoning with suspect 2. And we'd end up at the same conclusion. That the strategy of deny was strictly dominated by confess. So both players would end up confessing. Now, given the way that we've set this game up, we've said that there is a strictly dominated strategy, that we will never ever choose to deny. Well, given that we've only got 2 outcomes, if one of them we'd never choose to do, we'd never choose to deny, that means that the players will always choose to confess. And in scenarios such as this, if you have one single optimal strategy, something that you always choose to do, regardless of what the other player does, that is referred to as a dominant strategy. That means it's your best response for all possible choices of the other players. So it's a dominant strategy. So in this prisoner's dilemma, there is a dominant strategy. There's a dominant strategy to confess. Doesn't matter what your rival does, you always will choose to confess to the crime. And hence, the outcome of this game, the solution to the game, the most plausible outcome to this game, is where both prisoners end up confessing. Now what I want you to do, though, is reflect slightly on that. That was the game that we saw. And we said the outcome that we get, where there's a dominant strategy, both players will choose to confess. That's our equilibrium. That's the outcome. That's the most likely, the most plausible outcome we'll arrive at. Doesn't it strike you as a little bit strange? This means that both prisoners will spend 6 months in prison. Compare that, though, to that outcome there, where they both choose to deny. If they both chose to deny, they would each spend just 1 month in prison. So we can say, if our outcome, our most plausible outcome, is this one here, where they're spending 6 months in prison, that must be Pareto suboptimal. Remember what we did before when we looked at intermediate micro? We defined this concept of Pareto optimality. We have a Pareto efficient outcome or Pareto optimal outcome when it's not possible to make someone better off without making someone else worse off. Well, look at that outcome there. -6, -6. If we both choose, or they both choose to deny, they both get a lower payoff. Sorry, they both get less time in prison. They both get a better payoff. Therefore, what does that mean? It means we've made a Pareto improvement. We've made both players better off. We've made a Pareto improvement. And hence, it means that that outcome there, our most likely, our most plausible outcome, isn't Pareto efficient. It must be Pareto suboptimal. So, that then is a prisoner's dilemma, and how we'd solve it using that very, very simple principle. Well, what I now want to do is move on a little bit, because if only games were that simple, if only they were always strictly dominated strategies. So what I'm going to do is give you this very, very simple but abstract game. And in this game here, there are two players, player 1 and player 2, and player 1 chooses over the two available strategies of up or down, and player 2 chooses over the two strategies of left, middle, and right. And given these various combinations, the payoffs are just represented by these abstract numbers here, 0, 1, 2, and 3. So for example, if player 1 chose up, at the same time as player 2 chose left, player 1 would receive a payoff of 1, and player 2 would receive a payoff of 0. And all of the other cells have an equivalent interpretation. So that's our game, and that's how we would represent this static game in normal form. So what's the most likely outcome of this game? Well, we've said what we need to do is identify those strictly dominated strategies. Those strategies for which a player would never ever choose to play. Well, let's look for player 1 first of all. Player 1 chooses up or down. So if player 1 chooses up and player 2 chooses left, gets a payoff of 1. Or middle gets a payoff of 1, right gets a payoff of 0. So that's what player 1 could get if he chose up. A payoff of 1, a payoff of 1, or a payoff of 0, depending upon what player 2 does. Well, what would happen if he chose down? If he chose down, get a payoff of 0, which is less than 1, get a payoff of 0, which is less than 1, or get a payoff of 2, which is greater than 0. So what would player 1 choose to do? We choose to play up if his rival chose left or middle, but he would choose to play down if his rival chose right. So there is no strictly dominated strategy. A strictly dominated strategy is a strategy that always gives a lower payoff. For player 1, is there a strictly dominated strategy? Is one payoff always lower? The answer is no. So that idea that we've introduced so far doesn't really help us, because for player 1 there is no strictly dominated strategy. However, if we look at player 2 though, we know that the option of right is strictly dominated by middle. So just look at the payoffs to player 2. Remember, if we're looking for player 2, we're looking at the second figure. So I said look at middle and right. So player 2 either has a payoff of 1 or payoff of 2, or has a payoff of 0 or a payoff of 1. So if you play middle, you get 2 or 1. You choose right, you get 1 or 0. So you can see right always gives a lower payoff. Player 1 chooses up, you get 1 as opposed to 0. If player 1 chooses down, you get 0 as opposed to 1. So right always gives a lower payoff. So we can say then that right is strictly dominated by middle. And what did we say a rational player will never do? Play a strictly dominated strategy. So we know that player 2 would never ever choose to play right, because he could always do better by choosing middle. So we know he won't ever do that. So we could remove that as a viable option, as a potential option for player 2. Notice though, all I've done so far, I've talked about middle and right. I've said absolutely nothing about left. We're not looking at left. We're not concerned about left. All we're interested in, if player 2 had the options of middle and right, would he ever choose right over middle? From what we've seen here, the simple answer is no. Because right is strictly dominated by middle. All we're doing is making that pairwise comparison between those two potential strategies. And so, in that case, we know that middle would always be chosen in preference for right. So we can remove right as an option for player 2. Now, if player 1 knows that player 2 is rational, he will appreciate the fact that his rival would never choose to play right. And so, he could play the game as if it were this simplified form. Player 1 again chooses over up or down. Player 2 now only effectively chooses over left and middle, because he won't ever choose to play right. So that effectively is the game that the players are now playing. Now what I want to do is go back to player 1 and think, what outcomes does player 1 have? What payoffs does player 1 get? Well, for player 1, if he chooses up, he gets a payoff of 1 or 1. 1 if player 2 chooses left, 1 if player 2 chooses middle. But if he chose to play down, he would get a payoff of 0 in either scenario. In both cases, it gives a lower payoff. So what can we say? We can say for player 1, down is now strictly dominated by up. Down always gives a payoff of 0. Up always gives a payoff of 1. So what will a rational player do? A rational player 1 would never choose to play the strategy of down. And so we can remove that as a potential action for player 1. And if player 2 appreciates this, knows that his rival is rational, he'll know that his rival will never choose the strategy of down. And so he can remove it from his game set. And then the effective game that we have reduces down to this, where player 1 will always choose up, and player 2 chooses over the outcomes of left or middle. If he chooses left, he gets a payoff of 0. Middle gets a payoff of 2. So what will it mean? It means you will never choose left, you'll always choose middle. And so, what do we have? Well, the outcome of this game, we started off with 6 potential outcomes. These various combinations of up, down, left, middle, and right. Of all of these potential outcomes, the one that we're left with is this one here, where player 1 chooses up, and player 2 responds by choosing middle. And that process that we've been through is known as the iterated elimination of strictly dominated strategies. And again, it builds upon that very, very simple idea that a rational player will never choose a strictly dominated strategies. And so, in this game, using that idea of eliminating all of these strictly dominated strategies, we're left with a single, a unique outcome, where player 1 has a payoff of 1 and player 2 has his payoff of 2.